Hi, I'm Dr. Thompson, and in this video we're going to talk about Newman projections. So Newman projections are a way of thinking about a three-dimensional molecule in two dimensions on a piece of paper. And they're really useful if we're talking about different conformations of the same molecule. So we think about ethane. Okay, it's the simplest of the alkanes. It has only 2 carbons and 6 hydrogens. And if I look at it like this, like we would typically think about a wedge and a dash structure, such that this is going away from me, so it's on a dash, and this is coming towards me on a wedge. Well, we know that at room temperature, single bonds can rotate. Okay, they can rotate through different conformations. But if I look at it like this, it's hard to tell the difference in energy as I make these different conformations, okay, as I spin these molecules through this rotation. And so that's why we have Newman projections. Instead of looking at a molecule like this, the way we're used to, a Newman projection is going to turn it on its head. And it's going to look at the molecule like this, okay, down the carbon-carbon bond, so that we can't see the bond anymore. We can only see the 2 carbons and all the things that are attached to them. Now, if I turn it like this, we can see that right now, the hydrogens are eclipsing each other. Okay, this hydrogen is directly behind this hydrogen. Now, hydrogens are pretty small, so this isn't actually that high in energy, but it's lower in energy if I rotate it like this. Just 60 degrees gives me something called a staggered conformation. The hydrogens are now staggered from each other. Okay, there's a little more space between them. If I continue to rotate this, I can get to another eclipsed, and then another staggered, and then another eclipsed, and then another staggered. Okay, I can do this all the way around. And if I'm looking at it down the bond, then the difference in these energies is a little more apparent. Now, ethane is very small, and it doesn't have that much energy difference in eclipsed and staggered. But if we get to a slightly larger molecule like butane, okay, now I have 4 carbons. And again, if I look at it like I usually think about molecules, in a line and dash, there's not that much difference as I rotate all these bonds, okay? But if I look at it in a Newman projection, I'm going to take this molecule and I'm going to turn it on its head, so that now I'm looking directly down the C2-C3 bond. Okay, you can't even see this back carbon anymore. It's behind the first carbon. Now, if I look at it this way, I can see that my big group is very far away from my little group. And as I rotate through the conformations, I can rotate it like this. So now this blue one is sulfur, okay, or nitrogen. The nitrogen is directly behind the carbon, and so they have some steric interactions. But my 2 big groups are still kind of far apart. Okay, so this is higher in energy, but not as high as it could be. If I rotate it more, I'm in a staggered conformation. Okay? None of the atoms are directly behind any of the other atoms. All staggered conformations are lower in energy than all eclipsed conformations. Okay, it's better to be staggered. Everyone has a little bit of room. Now in this conformation, you can see that these 2 big groups are right next to each other, okay, 60 degrees apart. This is called a gauche interaction. Gauche comes from the French that means awkward. Okay, these are awkwardly close together. Like if someone came into the room and stood a little too close to you. Okay, it's just a little awkward. And so this is not a great interaction, but not the worst. If I rotate one more time, now I've got these 2 methyl groups banging into each other directly. Okay, this is not only eclipsed, these carbons are directly behind each other, I also have the 2 largest groups eclipsed. Okay, so that means that they have sterics are against each other. Okay, we have the 2 biggest things closest together. That's the highest energy conformation. If I continue to rotate, I get to another gauche interaction, but now staggered, so better. If I continue to rotate, I go through another eclipsed, and then back to how I started. The most stable staggered interaction, where the biggest group is as far from the other group as it can get. So now we have to learn how to draw these in 2 dimensions. I wanted to show you with my model set because I imagine most of you have a model set. But I also want to show you how this looks like when it's rendered on a computer, okay? So we can really see the 3 dimensions, and I can show you how the perspective is changing. So let's watch a short video. So this is our starting molecule, butane. Okay, and this is how we're used to looking at it. This is how we're used to drawing it on a piece of paper. But if we want to look at the different conformations of this molecule, okay, as the molecule spins, if we look at it like this, it's not that easy to tell the difference in the conformations. And so what we do is we turn this molecule on its head. So I'm going to pause it and then I'll restart it. Okay, so we're going to turn it like this so that carbons 2 and 3 are directly on top of each other. Okay, so we're used to looking at it like this, and now I've turned it like this. And I'm going to let it start rotating again so that you can see the different conformations. Okay, and so as it rotates through 60 degrees, we can see eclipsed and staggered conformations. So I've paused it again to talk about two things. One, this is the most stable conformation. We have the biggest group as far away from the other biggest group as it can get. And when we look at this, okay, because those two carbons are directly on top of each other, okay, this black one and the one behind it, what we look at when we draw it is the front carbon has 3 things attached. These can be carbons or hydrogens or any other atom. And then the back carbon has 3 things attached. Okay, so the Newman projection just looks like these 6 things all coming out of some center carbon. Okay, and that's why it's weird for some students to get used to, because we're used to seeing all the bonds, but when we turn it for the Newman projection, we can't see the bond anymore between carbons number 2 and carbons number 3. But what we can see now very clearly is the differences as this molecule rotates. So now this is a Gouge interaction. Okay, so the two biggest groups are 60 degrees apart from each other. And as we keep rotating, we go through an eclipsed conformation. Now they're on top of each other. That's the highest energy. And then Gouge again. Okay, another staggered conformation. And then here eclipsed. And then we're back to the most stable staggered conformation. Okay, and so as you watch this, you can see as it's moving that all we're actually doing is rotating this bond. Okay, the different Newman projections are just rotations around that bond. So there are 2 main skills that I want you to have at the end of this video. One is to be able to go from a wedge and dash structure to a Newman projection. And the other one is to be able to take that Newman projection and rotate it to the lowest energy conformation. So let's start with an example. First, I'm going to draw a molecule in wedge and dash. So we'll give ourselves a wedged bromine and a dashed isopropyl. Okay? And we're going to draw the Newman projection from this perspective, looking down the atoms like this. So this atom, and we're looking down this bond. Now here's where I'm going to ask you to do something a little silly, okay? I want you to pretend like there's a tiny alien right here. Okay, he has a lot of tentacles because all aliens have lots of tentacles. He's very, very tiny and he's looking down this bond. And we're going to draw this Newman projection from his perspective. Okay? And so if he's a tiny alien and he's right here, if he looks up, he's going to see a line to a methyl group. And remember, we have a wedged bromine, which means we have a dashed hydrogen. And a wedge means it's coming out of the board towards me, and the dash is going into the board away from me. So if I'm a tiny alien and I'm standing right here looking up this bond, something that's coming out of the board is going to be on my right. And so the bromine is going to go on my right. And if I'm here, the thing that's going into the board is going to be going away from me on my left. So on my left goes the hydrogen. And then we're going to draw a bigger circle. This represents the back carbon. Okay? This one represents the front carbon. This represents the back carbon, or this one. And so if I continue to look down that bond, okay, I know I have a dashed isopropyl, which means I have a wedged hydrogen. And so if I look down that bond, I'm going to see the hydrogen is projecting out of the board towards me. That's on my right side. And so on my right side, I'm going to put a hydrogen. Now that wedge means it's going into the board away from me, and so it's on my left side. So on my left side, there goes an isopropyl. And then straight down, there goes a methyl. So this is the Newman projection for this molecule. Okay? This is as it sits here. Now this is not necessarily the most stable conformation. The most stable conformation gets the two biggest groups as far apart from each other as they can be. So first let's look and see what's the biggest groups. On the front carbon, the biggest group is the methyl. It has the most atoms attached to it, okay? And generally for this purpose, that's going to be the largest group. And on my back carbon, I have to choose between methyl, hydrogen, and isopropyl. So isopropyl is the largest group. So as it's drawn here in wedge and dash, the largest groups are next to each other, okay? Remember that word is gauche. That's not the most stable conformation, but I can rotate these because I have free rotation to get to the most stable conformation. And so to do that, you can either rotate the front or the back. I think it's easiest to keep the back still, so that's what I'm going to do. So first thing, I'm just going to redraw the back carbon exactly the way it is right now. Okay, and then I need to rotate the front carbon until I get the biggest groups the farthest apart. So that means I'm going to take my whole front carbon and I'm going to rotate it one position to the right. I still want to keep it all staggered, but instead of my methyl being up, I'm going to move it one over. And to do that, the bromine has to move one over. And to do that, the hydrogen now goes up here. Okay? And so my two biggest groups are now as far apart from each other as they can get. Now you might point out that I still have two methyl groups next to each other. Okay, that's not great, but it's still lower in energy to have the largest groups further away. Okay, this is better than when I had the methyl next to the isopropyl. Okay, so that's how we draw the Newman projection from this perspective. But what about if I asked you to draw it from this perspective? Because I could have, right? And so we're going to draw another tiny little multi-tentacled alien. And we're going to look at it down from this perspective because I could look at it any way I wanted. And the Newman projection is going to look different depending on the perspective. Okay? These are perspective drawings, so the perspective matters. So if we look at it from this side, now my alien is going to see a methyl group pointed down. My marker might squeak a little more lower on the board. And so he's going to see the methyl pointed down. Now remember that the hydrogen is coming towards me and the isopropyl is going away. So from his perspective, the hydrogen is now on his left, coming towards me. And the isopropyl, which is going into the board, well, from his perspective, that's on his right. And if you continue to look down this bond, now I have a methyl group going directly up. Remember, this bromine is coming out of the board towards me, so now it's on my left. And that puts the hydrogen going away from me and on my right. Now, if we compare these two Newman projections, we're going to see some interesting things. First is that they're flips of each other, right? The isopropyl and the hydrogen are still on the same side, but they started on the left side and now they're on the right side. Okay, a lot of students make the mistake of memorizing, well, wedges are always on my left or dashes are always on my right, and that's not the case. Okay, it matters what your perspective is. And the other thing I want to point out is that they are on the same side as each other, okay? So wedges, the bromine is wedged and the hydrogen is wedged, and the bromine and hydrogen are on the same side, okay? Even though they're left and right switching, the bromine and the hydrogen are still on the same side as each other, okay? Now this is still not in the lowest energy conformation, and so if I wanted to draw the lowest energy conformation, I would have to do this again. Keep the back still and rotate the front until I got the isopropyl which is the largest group on the front, and the methyl, which is the largest group on the back, to be as far apart from each other as they can be. But it's the same process as for this. Okay? So go do lots of practice and it should get better.